Hi guys. So I think I will start a couple of minutes early because I don't think I can finish up into the 25 minutes which this session was allocated in. So I'm Ramnandan. I'm from Cosmos DB. I'm an engineer, but we have this very interesting team called the Ninjas, who we do a lot of customer engagements. And I also own the Spark connector and all the other OSS bits related to Cosmos DB. So that said, let's jump right in. OK, so by show of hands, how many of you don't know Cosmos DB or have never heard about it before? OK, so it's a few of you, but which is why I actually have the next couple of slides. I actually want to spend the majority of this session talking about data science aspect of Cosmos DB, but just for the sake of a few of you who don't know about Cosmos DB, it'll be good to go through what Cosmos DB is and what sets us apart from the other data offerings in Azure. So as you know, Cosmos DB is Microsoft's globally distributed multi-model database service. What that means is we are a foundational ring zero service in Azure, which means when a data center comes up in Azure, we are there in the next 13 minutes, which internally, which hence allows you to replicate. So today we have you have planet scale applications. With planet scale applications comes the need for a globally distributed database. So which means when I write data to a specific region, say in US, I want to have my data replicated natively to all other regions in the world. So which is what Cosmos DB allows you to do. With a click of a button, you can now replicate your data at the speed of light to all other other regions you choose to replicate your data to. And hence, our SDKs are very intelligent in that they automatically decide which is the nearest read region they should go read the data from. So it's basically no effort from your side in terms of replicating that data across the world. And then comes low latency. So while we have now distributed your data all across the world, you now want to access that data relatively really quickly. So we essentially are very proud of the fact that we guarantee single-digit millisecond latency. We have financially backed SLAs for both our reads and writes. Reads are at the 99th percentile, less than 10 milliseconds, and writes are less than 15 milliseconds. But that's just the 99th percentile. On average, most of our reads are less than a millisecond, and our writes are less than 6 milliseconds. And all of this comes because we are backed by a write-optimized latch-free database engine, which runs on SSD storage. And then the very nice thing about elastically scalable storage, which is you have terabytes or petabytes of data which you have. And today, if you try to store that, run your own database on-prem, you have to think about how many VMs you need to provision, how much spare SSDs you need to allocate, and all of that. So we take away all of that hassle away from you, where you only pay per GB which you consume, and we handle all of the partition management and overhead associated with storage and all of that. And then comes elastically scalable throughput, which is essentially today you may have an application which has only 1,000 requests per second. And tomorrow, you may want to scale up to 1 million or hundreds of millions operations per second. Now, you do not, again, need to go and configure anything on your end. You can, by the slide of this unit called request units, you can basically configure how many operations per second you want to support on top of the database. And again, here, you pay by the hour, so you only pay for what you consume. So this is an example of some of our e-commerce customers like Jet.com, Walmart, who basically, on Black Friday, they need to go up by 5 times because they need to handle 5 times the load. And hence, by just the click of a button, they can scale up. And then after Black Friday, they can scale down. And they don't have to over-provision either storage or compute at any time. And then we have financially backed SLAs for not just our availability, which is at 5 nines, but also for our latency, for our consistency, for our throughput. All of that we show on the portal, and you can call us out if you think we have not satisfied the SLA which we say we provide. And then we again provide 5 different types of consistency models with which you can interact with your database. And again, this is state of the art because most of the other NoSQL offerings out there, again, provide either extremes where they provide you only 2 consistency models or a very large number of consistency models. But we, based on feedback we've received from all of our customers, we have these 5 well-defined consistency models you can choose from on the portal. And then we are a multi-model database service, which means, so we see data out there comes in different flavors. You can have data which is naturally document format. It can be key value. It can be graphs. It can be columnar. So we don't want you to, we don't want to restrict you to store that in a tabular format. We want you to store the way the data is actually to be stored. So we support all of these data models, which can internally be, which can be accessed through multiple APIs. So we support access through a SQL-like API, a JavaScript API, MongoDB API, Cassandra, Gremlin, and more to come. So what that means is if you have a Mongo or a Cassandra application which is on-prem, with relatively no code change, you can just change the connection string and move to the cloud, and hence get all the other benefits which we spoke about, which Cosmos DB provides. And the other really nice thing, if you come from a relational world, is again schema and index management, which you probably spend a lot of time on. Again, we do all of that natively, so you just have to store the data, and we automatically index all the fields in your data. So you can query them without having to maintain your own indexes. And we have a very nice paper out there which talks, and if you come from more of a financial side, in terms of what's the total cost of ownership of Cosmos DB versus DynamoDB from Amazon, or just like hosting Mongo or Cassandra on-prem, we have a very nice white paper out there which compares the total cost of ownership, and we essentially the crux is that we are cheaper. Yeah. So now, okay, this was all about Cosmos DB, but why you came here was for real-time data science on top of Cosmos DB, right? And so essentially that's where our Spark connector comes in. We have a native connector between Spark and Cosmos DB. What that allows you to do is, so you know the concept of Spark partitions, right, and Spark worker nodes. Now, we essentially have, your Spark partitions can now natively talk to Cosmos DB partitions and can hence leverage the Cosmos DB index directly, rather than going through any other external overhead. What that allows you to do is push down filtering. So for example, if you have complex queries which you're running on top of your Spark data frames, all of those, instead of pulling in all the data from your database into Spark in memory, you can now push down a lot of your computation down into the database. And we've been in GA, the Spark connector has been GA since last year, and we have a large number of whale customers who are essentially in production with our Spark connector. So this is how our the architecture of our Spark connector is. So on the left, you have a Spark cluster. As you know, it has a master node, and then you have worker nodes. And on the right side, we have Cosmos DB. If you spin up a Cosmos DB container, be it SQL API, Graph, Cassandra, Gremlin, whatever, you basically have a similar architecture where you have something called a gateway node, which essentially addresses all your metadata operations. So if you want to get what the database name is and all of that, all those operations are served by the gateway node. And then you actually have your data nodes, which house your data. And that's how we provide this elastic scale out. So if you go from 100 GB to 1 terabyte, we basically stand up additional such shards or data nodes which house your data. Now, how the Spark connector works is the very first time you configure Spark to talk to Cosmos DB, the master node talks directly to the gateway node of Cosmos DB to understand how many data nodes are there, what is the partition map, and all such metadata, which is returned back to your Spark master node, which then sends that information down to the worker nodes. And with that, your worker nodes are now directly aware of Cosmos DB data partitions, and hence all your Spark computation, your distributed compute, directly talks to the data nodes. So there's a 1:1 mapping between Spark executors and Cosmos DB partitions. So there is no concept of a single bottleneck. So if you're basically doing any sort of aggregations, all your aggregations are now in parallel. So you have a distributed compute engine directly talking to a distributed storage platform. And the other very important thing which you need to take, which you can take advantage of when you're running, say, stream applications on top of Cosmos DB is our change feed. So when you have a fire hose of data which you're pushing into Cosmos DB, we have this native feature called a change feed. You don't pay for it. It comes free of cost. It's available to every single collection you spin up. Is nothing but as you push data into Cosmos DB, you have a queue, which is an in-order list of all the changes which have happened on your collection. So as you create documents, or as you update documents, you now have, think about it as like a queue of all the changes, which you can then subscribe to. So which now allows all your batch and stream compute jobs, be it Spark, Storm, Hadoop, Stream Analytics, all of them can now listen to that change feed. So this is a way of streamifying your batch data. So as you get a lot of data coming in, you now have a notion of a stream of those changes which you can then listen to. So this is the main part of this talk today, which is about Lambda architecture. So how many of you are actually aware of Lambda architecture, or have you been using Lambda architecture? Okay, cool. That's a few of you. So Lambda architecture, for those who are not aware, is basically a classic scalable and fault-tolerant data processing paradigm when you want to mine massive data sets. So the idea is very simple. So you have data coming into your platform. What the Lambda architecture suggests you to do is push that data. So you have three different components of the Lambda architecture. One is your batch layer, you have a serving layer, and then you have something called the speed layer. So as you have data coming in, you push that data to both your batch layer and to your speed layer. Your batch layer essentially consists of a master data set, which, think about it, is just like a ledger of all the data which you have, which is like an immutable append-only set of rows. So you don't do any aggregation on that. It's just the set of changes which have come into the documents which have been created, or the set of updates which have happened. This is just a ledger of all of them. Now, this batch layer is also responsible for then pre-computing any aggregations you can do on that. I have a demo which showcases this. But say, for example, you have a large amount of Twitter data coming in. Now, each of the tweets are individual documents. But what your end users may be interested in is a certain aggregated view of the set of data which has come in. So you can then perform those aggregations and store them in the batch view, in the serving layer. So essentially, your users or your clients essentially hit the serving layer for all your fast queries. So at the query time, you're not performing any aggregations. You've already aggregated and stored that data, so your queries are really fast. Now, the speed layer essentially compensates for all this processing time, because your batch layer has to do these aggregations, which potentially could be over days or over years. Now, this is not going to be real time. So if you want to do real-time aggregations on only recent data, so you want to, say, do sliding window aggregations on the last few seconds or the last few minutes, you don't want to have to directly query on top of your batch data, right? What you just want to have is you have some stream of data coming in, and I want to do aggregations on top of that. So that's where the real-time view comes in the speed layer. So what the Lambda architecture says is, when your user supplies a query, you individually ping your serving layer and your speed layer, and then potentially even combine the results and submit the results back to the user. Now, this is great, but we think we've solved the problem to a better degree, which is essentially this. When you bring Cosmos DB into the picture with Lambda architecture, you no longer need to push your data to two separate sources. So there are multiple problems we've heard from our customers as well with previous Lambda architectures, where if you had a separate batch database and then a separate data store for your real time, which is essentially that you now have to be responsible for maintaining 2 different data pipelines to your master data set and then to your real-time view data store as well, and also about data consistency. So if you're now pushing data to 2 different data stores, how do I ensure that if one single write failed, say to my batch view, how do I ensure that the record is not inconsistent or is present or absent in the other data store? So, which is where what we propose is, when you're talking about Lambda architecture with Cosmos DB, you just push your data to a single master data set, which is a Cosmos DB collection, which is in your batch layer. Now, and that's where change feed comes in, which is that change feed essentially is that magic sauce which streamifies your batch data so that you can then listen to that for real-time views. And I'll come back to that in a second. So the next part is the batch and the serving layers, right? So now you have data coming in and you've pushed that into a Cosmos DB collection, which is your master data set. Now, I want to perform some aggregations on top of that, and that's where Spark comes in. So you can now run periodic jobs which do aggregations, and then store that aggregated view in a separate Cosmos DB collection, which your users or your clients can then hit directly for faster queries. So you have pre-optimized what your queries are going to look like. So now I have optimized the structure and the aggregated view so that my queries are can now potentially even just be direct reads rather than queries. So they can, with that 1 millisecond, you can now do 1 millisecond or a couple of single-digit millisecond reads. So that's basically about the serving layer. And then comes the speed layer, which is our Spark connector supports structured streaming. So structured streaming is, so the really nice thing about Spark is that it supports both batch as well as streaming applications very easily. So there's the concept of structured streaming in Spark, which is essentially near real-time stream processing. And if you've been following the Spark commits recently, they're also working towards continuous processing, which is essentially going to be real-time processing, which you can then do on Spark. So, and why I'm suggesting using Spark structured streaming instead of actually using a native real-time streaming paradigm like Apache Storm is now you can write your business logic in a single Spark application, and with very few lines of code, just change between a batch and a streaming mode. And I can show you an example. It's basically very similar. Instead of, if you do, in batch mode, you do spark.read, and in streaming mode, you do spark.readstream. And our connector does all the other magic under the hood. So when you do spark.readstream on Cosmos DB, it utilizes the change feed to read your batch data in a stream mode. So basically, when you read data in batch or stream mode from Cosmos DB, we do all the magic and hard work inside the Spark connector. So I definitely suggest that you go give the Spark connector a try if you still haven't. So now once you've done all your streaming aggregations on Spark structured streaming, you could potentially also persist that data. So say you have done sliding window aggregations on just the last couple of seconds or last couple of minutes. Now you can potentially allow your end user to directly talk to Spark and provide a REST endpoint which can receive that data, but also you may want to persist that data. So which is why we also say you can just, within the same Cosmos DB database, you can just spin up another collection which houses your real-time aggregated views. So this is what we say is the new Lambda architecture paradigm with Cosmos DB, the re-architected version, which is you don't have this concept of a separate batch and a separate speed layer. But what you do is, as you get new data, you just store it into a single Cosmos DB collection. And you can then run, as you can see, you can run your pre-compute batch views on top of your master data set and store them back in a separate collection, which your users can then hit. And you can also utilize change feed to do Spark structured streaming on top of that. and hence and persist those results as well. So hence, if your user submits a query, you can decide if it's a batch job, hit the pre-computed batch, or if it's a real-time view, you can just hit the real-time aggregated view. So, and that's it. Now we can just switch into like a demo. Okay, we have 5 moments. So this is the cool. So this is essentially, I have separate demos for basically showing the batch layer, and then connecting the batch layer and the serving layer, and then how do we use change speed to do the speed layer. So in this example, we have this out on GitHub as well, so you can go check this out later. So what we do here in this demo is we have a separate console application which listens to Twitter for specific hashtags, like we listen to AI, machine learning, big data, databases, and we then push all those tweets into Cosmos DB, and that's where. So this is how the Spark connector works. It's super simple. What you have to do is just configure what your Cosmos DB endpoint is and what database and collection is, and you can then specify a custom query. So here I say, just go get me all the IDs created at user screen name and all such other properties. And I can run this again, so basically, as you can see, we have, for example, we have 1,000. I just ran it a couple of minutes before I started the demo. So we have 1,300 tweets which have come in recently. And now Spark SQL, as a lot of you may be aware, is an extremely powerful, expressive, declarative query language. So you can now run Spark SQL queries. So here I'm just trying to just do like a top of, just show me the top 20 records which I have pulled from Cosmos DB. So as you can see, these are just some of the tweets which have come in recently. And then I want to do some aggregations on top of it. Now, each of those tweets, for example, has a set of hashtags associated with them. So I want to do some aggregation to say, tell me what are the top 10 hashtags which I have received which I have in my database, right? Now, this application has just been running for a few minutes. So we only have 1,300 tweets, but potentially you can have millions or billions of such tweets inside. So now I have such billions of tweets, and I want to say, give me the top 10 hashtags. Now, instead of pulling in all the data from Cosmos DB into Spark and then running this SQL query, what we do is essentially when you write any such SQL query, we internally, the Spark connector essentially pushes down a lot of those filters and predicates, the projections down onto the database. And hence, you essentially don't require that large a cluster even if you're processing gigabytes or terabytes of data. So, Azure Databricks is really awesome if I'm sure all of you have given it a shot. The notebooks, Databricks notebooks allow you to do a lot of exploratory analysis. Then, okay, so now we want to talk about, so I have this huge amount of data in this Cosmos DB collection, which is my master data set. How do I aggregate that view and push that into another collection, which is essentially my serving layer? So in this example, what we do, again, very simple. Apart from a read config, I also have something called a write config, where now it's the same as the read config, except that I have a separate collection here, which is the aggregated view, which is called tweets by tags. What that does is essentially the same thing, which is I want to identify, like I want to have every day, I will go run an aggregated view on top of that, saying on that day, until that day, what is the top 10 hashtags and how many such tweets did I get? This is the most simple aggregation you can do just for the demo, but you can do potentially in your business logic, you could do a lot of such complex aggregations, right? So now you do that aggregation, and then with a single line of code, you just write that data back to a separate Cosmos DB collection. So you just do dataframe.write.cosmosdb, and this internally uses the Spark connector, we've also introduced bulk import feature into the Spark connector. So if you're trying to write, say, a gigabyte or like a terabyte of data, now the new bulk executor feature, which we've released in Cosmos DB, shows a 10x improvement in ingestion performance, and that comes natively as part into the Spark connector now. So if you're writing a gigabyte or a terabyte of data, it's going to be really fast. So now I've written that data into a Cosmos DB collection. So let's just take a look there. So this is the database which I've spun up, which is called Twitter database. I have two separate collections. One is the Twitter collection, which is your master data set. And so this, for example, you see it has each of the documents are huge tweets. And then I also have this aggregated view, which essentially, as you can see, is just an aggregated view of, it just stores for every hashtag, how many tweets did I see until then. So as you can see, this is super simple, and now your users can now do very simple, fast queries on this aggregated view, rather than running their queries on those massive tweets which we had, which was part of our Twitter collection, right? And then comes the speed layer. Now, all of this is great. So if I want to run queries on, say, what are the top 10 hashtags in my tweets collection over the last few days or last few months, what I showed you works. Now, what about if I want to run queries on saying, as I'm talking right now, what are the, in the last couple of seconds, how many tweets did I see with, say, a machine learning hashtag? Now, that's where the streaming layer or the speed layer comes in. Again, with speed layer, very simple. You just say what is the collection you want to listen to, and then you just say spark.readstream. Format Cosmos DB provider .load. And that essentially uses the change feed to listen to the set of changes. Now here, as you can see, the stream data, if I just do a print schema on what are the changes, you can see that I get like created at, favorited, and all of the, whatever the schema of a tweet is. Now, as you can see, I'm running this Spark job at the moment. So essentially what the structured streaming does is you can configure at what interval go and listen to the set of changes which have happened. So you can set 1 second, 50 milliseconds, 1 hour. So basically structured streaming at that period of time goes and fetches the results from change feed and runs your aggregations on top. So in this example, what I'm just trying to do is, as I speak, how many tweets am I seeing for every different type of language? So here, so that's what my query here tries to do. And it basically persists that in memory in this specific example, because I say format memory, but if you can just change the format to Cosmos DB, it will then persist the real-time aggregations into Cosmos DB as well. So in this example, if I just run the counts, I see again, for English, majority of the queries are coming from English, but then I have a huge, I have counts of tweets from all other languages as well. So this is basically how we, this is just a very simple demo, but we have customers in production who are using this in a very complicated manner as well. And we're happy to if you can reach out to us on Ask Cosmos DB, or you can reach out to me directly. With your specific scenarios, we can work on how we can enable Lambda architecture there. So that's it. I think I have a couple of more minutes, and we don't have a lot of time now, but we also have this demo out there, which again goes through a little more on if you want to do, if you use graph frames. So graph frames in Spark are essentially a methodology for you to solve graph problems. So if you want to run PageRank, I want to find structural motifs, I want to run basically any graph computation algorithm on top of data which is already in Spark. You can then construct your graph frames. So essentially, you read your data from Cosmos DB, and let me show you a quick example. So these are you can go look at all of these. So we have a lot of other examples out there. So basically, this is how do you build up a graph frame. That is, so I've read data from. So okay, the scenario is this. I have airport and departure delay information in Cosmos DB. And I also have a separate blob store of metadata information about airports. Now I want to, so I pull the data from both Cosmos DB and blob into Spark, and then I construct what my set of vertices should be and what my set of edges should be, and then I define a graph frame. So I define something called a trip graph. Now you can do a little more interesting things on top of this, saying you can just do like, which flights departing from Seattle have the significant delays, and you can do like degree-related queries on top of your vertices on the graph, which is here I can say which is the most important airport, which is in terms of like how many flights are in and out of that airport. Or you can also do now, if you want to do breadth, like depth first scan, breadth first scan, if you want to find the shortest path between two airports. Now all of this again directly runs on top of graph frames. Graph frames are built on top of data frames, and hence again all the push down filtering can still work on Cosmos DB data. So essentially you can use the SQL API again to build this graph frame on Spark to do your graph computations, or also we also support the graph API on Cosmos DB. So if you think your graph, if they are not that complex analytics queries, you can directly run your you can express your queries as Gremlin queries and run them on Cosmos DB. And then one last thing, again, Spark comes again with this MLlib, which is, it has a huge, very diverse set of machine learning libraries available to you, which you can now run again on top of the data you've pulled from Cosmos DB. So in this scenario, what we try to do is essentially predict whether a flight will be delayed or not, depending on which airport it's originating from and where the destination airport is. It's very simple. Like one of the simplest examples we show, we build a logistic regression model on top of the data, and we essentially. So for example, and then we show you some of the evaluation. So for example, here we show the accuracy which the model has achieved. And then we also show you like the true positives, the amount of false positives, and all of that can be visualized very neatly on top of that. So that's it. So that's basically what we wanted to show. There is a lot of other nuances, but again, in 25 minutes, I don't think we could go into further details. But we're very happy to talk to you further, and we're excited if you can go try the Spark connector on top of Cosmos DB. Yeah, thank you.